extreme precipitation, floods, and droughts are kind of all embedded in what I'm going to be talking about here. So, the hydrological cycle, the water cycle, is probably, a lot more important even than temperature, even though we spend the most time talking about temperature, just because that's the first direct influence of increasing greenhouse gases. But if you think about, how important water is to life and to society, like any changes in the water cycle are going to be a big deal. And so you can kind of just see that on a diagram like this, that, we use, our snowpack for our drinking water. It flows into reservoirs. Changes in rain and precipitation are going to be really important for ecosystems, the entire terrestrial biosphere. Remember our photosynthesis and respiration equation. We need that H2O in our photosynthesis equation that gets everything going as far as life is concerned. So we need this input of water here. Agricultural systems, all of our food requires water, and energy production requires water. Waste, we need running water in our homes for everything we do. And then, of course, when we get too much water, that's not good either, right? So this is a picture of suburban Houston after Hurricane Harvey. So obviously very, devastating flooding after that, billions and billions of dollars in damage. And so any type of changes in extreme precipitation or floods are going to be a big deal to us. And then the opposite, droughts, can be very detrimental to our crops. So this is, it's a little bit confusing in terms of what climate change is expected or is doing to the hydrological cycle. If temperature was confusing, the water cycle is more confusing. So like here's just some headlines that I just pulled with a quick Google search yesterday. So climate change ravaged Colorado and the West with heat and drought in 2020. And so this year may be worse. So that's kind of climate change causes drying type of thing. Here's another one, drier European summers projected under climate change. Okay, so that's kind of indicating, drier, less moisture. But then here, this is just from, within the same time period, warmer and wetter climates amplify carbon release, talking about in the Arctic. And then here's another one, as climate change increases flooding, Massachusetts likely to see damaged property costs surge, report says. So we have what seems like kind of contradictory effects from climate change. Like, does it cause dryness? Does it cause more moisture? Does it cause droughts? Does it cause floods? And, does it just depend on location and time of year and all of these other considerations? And so what I want to do today, and maybe leaking into next time, is to kind of sort this out as best I can. So it turns out it is complicated, and it does depend on the location and time of year and a bunch of other considerations. But I want to summarize in as concise a way as possible what the kind of baseline first order changes we expect from the water cycle are under climate change. So let's first just look at the basic theory of how the water cycle might change as it gets warmer. So I'm going to go back to my 2D simple diagram of the climate system. So just to remind you, I've spent a lot of time on this talking about the Earth's energy budget, where in this case the arrows were shortwave radiation coming from the sun and longwave radiation coming from the Earth. We also spent last semester a couple lectures in the same diagram talking about the carbon cycle, where the arrows, instead of being shortwave and longwave radiation, were gigatons of carbon moving around the Earth system. And so now I'm going to do the same thing, but just talking about the water cycle, where now the arrows are movements of water molecules. So Thanks. So where do we start? Well, I don't know if you remember from, I don't know, 6th grade or something. We start with evaporation, right? The sun is giving us energy, which causes water in the ocean mostly. Most of our evaporation comes from the ocean. It's causing those water molecules to change from their liquid form to gaseous form and to go into the atmosphere. And what happens is the atmosphere gets colder as you go up, right? You have snow-capped mountains. It's cold up in a plain. So as it gets colder, the water wants to condense back into a liquid. And so that's what clouds are. Clouds are liquid water or ice water, little droplets of liquid water. They're not gas. We can't see water vapor or water in gas form, but we can see clouds because they're in liquid form. So evaporation, condensation, and then what's the third one? We've got precipitation, right? So it comes back out of the atmosphere. So we got water constantly going into the atmosphere and water constantly coming out of the atmosphere. And almost all of our water on land is just evaporated water from the ocean condensing, and then those clouds and water vapor moving towards the land where it precipitates out onto the land. And all of our lakes and rivers are basically former ocean water that was rained onto land. And so our rivers then run back down to the ocean, which in hydrology we usually call runoff is the term for that. But then we also have, water in the ground represented here that comes from precipitation that was originally in the ocean, or water that was in the ocean. And then we also have evaporation from the land. Okay, so this is the water cycle. This is climate, evaporation, condensation, precipitation. And so in the current climate, this is just a map of the average precipitation for each month of the year. And so this is kind of just interesting in its own right. So we can see, the most precipitation is kind of right along the equator. And we see that it moves up into the northern hemisphere in our summer and then down into the southern hemisphere in their summer. So it kind of follows the sun. This central location of thunderstorms is called the Intertropical Convergence Zone. And it's kind of just, it's just following the kind of solar noon as that progresses throughout the year. And we can see some interesting things, like we can see the Indian monsoon. So in the summer and fall, they have very wet time period, and it's kind of just that intertropical convergence zone moving up into India, and then that's enhanced by the fact that it's land surrounded by water. You can see things like, if you ever watch like Discovery Channel type documentaries on African savanna wildlife, they talk about like the dry season and the wet season, and you can see that there's the wet season and there's the dry season. You can see our wet season and dry season, so our winter and our summer, and that's very different than the East Coast of the United States, where if you're in New York, there is no dry season and wet season. Their seasonality is almost entirely in temperature, right? They have cold winters and warm summers, but kind of the same precipitation all year round, where we have very much seasonality in precipitation. And so the reason that we have these white spaces of low precipitation is kind of just it's the opposite of this enhanced precipitation at the equator. So what happens is where the sun is most intense, that's where the convection is, that's where the big thunderstorms are. And then that air needs to come down someplace else. And so basically you have air that rains out all its water, and then it comes down on both sides of the equator, very dry, and suppresses any thunderstorm activity. And so that's why you have all of the Earth's major deserts are in these zones. So the Sahara Desert, and then there's more deserty regions down here, Australia, and then our southwest desert as well as, and these kind of down, it's called the down descending branch of the Hadley cell. And so in California, we're kind of in that in the summer, and then we're out of it in the winter. And so that's where our precipitation seasonality comes from. Okay, so that's just climate, not climate change. So let's talk about what does the water cycle do under global warming. So one thing that's super important for this, for thinking about what the water cycle does under global warming, is to first review, I'm not sure if I've mentioned this much before, but review the fact that land warms more than the ocean. So this ends up becoming important. So land warms about 50% faster than the ocean. And this is a climate model representation of that. We see this in observations as well. But this is the ratio of local warming, so wherever point you are on the globe, to the global average warming. And so the ratio, if that's above 1, then that means local warming is greater than global warming. And so we see over most land locations, we have these colors that are greater than 1. And so on average over land, it's about 1.5. It's about 50% more warming over land than over the ocean. So just keep that in mind. Okay, so as it gets warmer, what would you guess? Would you guess would you guess evaporation increases or decreases? So, okay, so I'll just put this on here. Let's just say it warms, it's gonna warm 1 C over the ocean, 1.5 C over the land. And as it warms, evaporation increases. And what rate does it increase at? It increases at 3% per degree Celsius of warming. So I'm going to make this flux bigger. So we have more evaporation going into the atmosphere as it gets warmer by 3% per degree Celsius. So we're at about 1 degree Celsius right now. So we have about 3% more evaporation now than we did prior to the Industrial Revolution. Now, something else that happens is you may have heard that warmer air can hold more water vapor. So that's kind of a different process actually than this 3% thing. But I'll just put that on there as well because this becomes important for something else. So the atmospheric reservoir, we'll call it, that's just, how much water vapor can the atmosphere hold? Reservoir just meaning, how much can it hold? That increases at 6% per degree of warming. So I'll put that here, that let's just say that this represents that we get plus 6% moisture in the atmosphere for 1 degree Celsius of warming. And then we're gonna have 6% more over here as well. So precipitation then globally, if what's going in is increasing by 3% per degree Celsius of warming, then what's coming out is going to be the same thing. Because we're not just like going to be piling up water. We're not just going to move the ocean to the atmosphere. We're going to have a balance, right? Where whatever's going in is going to be coming out. So 3% more precipitation is going to be occurring, and you have kind of 3% more advection of moisture onto the land and 3% more precipitation on land as well. And then you get, roughly 3% more runoff. So you get more, there's just on average over the whole globe, not necessarily at any given location, but you're going to have more precipitation over land and more runoff, more water in your rivers on average. But this is the important thing. The land warms more than the ocean. So I just increase the precipitation on the land by 3% because the evaporation, which mostly comes from the ocean, increased by 3%. But the land evaporation, this component, what's going into the atmosphere from the land, that is going to depend on the local land warming, not on the ocean warming over here. So this tends to increase more than 3%. So the evaporation over land is controlled by the warming over land, where the precipitation over land is really controlled by the warming over the ocean, because the source of that precipitation over the land is the evaporation that's coming from the ocean. So we have this mismatch here where this increased, the precipitation increased by 3%, but evaporation on the land increased by more than that because the land warms faster than the ocean. So what does that mean? That means that we expect on average precipitation to increase over the land. You have more water coming down on you, but despite that, the land dries because evaporation is increasing more over the land than precipitation is increasing. So represent that by, I used to have 3 water molecules here and I'll delete 1. So we expect, in a lot of locations anyway, the land to dry out, to become more arid as the temperature gets warmer. And you notice these aren't huge numbers, 3%. I'll show you what soil moisture looks like. So you can have this huge variability from year to year that's much larger than 3%. And so when we look at like historical records, and I'll show you some, you can't necessarily see this very well, but this is all pretty solid kind of fundamental climate physics. So we really do think that this is going on in the background, even if it's not like super, if it doesn't jump out at you by looking at the data. But I will show you some maps of what this looks like moving from theory to modeling. So let's look at each component one by one. So looking at first at precipitation change as it gets warmer, and then evaporation change, and then basically how dry the land is, which gets represented by soil moisture, we call it. Okay, so precipitation change looks like this. This is a map of precipitation change, again, under this kind of high emission scenario in 2100. And this is change. So we're looking at anything that's green is more precipitation, and anything that's brown is less precipitation. So I just told you before that precipitation increases by 3% per degree Celsius, but it's not universally the case. So even on land, it's on average about 3%, but there are some locations like around the Mediterranean and Europe, and in Mexico here, and then the Amazon is a big concern, where precipitation itself is projected to decrease. And this is like, you can see the pattern really well in a map like this, because this is a very high emission scenario, and you're kind of averaging out all of the random weather noise. But this is if you kind of squint, this is the basic picture that we expect. And so this pattern, if you notice, like what we looked at before, this was this is the pattern of existing precipitation, right? It's most at the equator, and then we have this relative area of little precipitation in the subtropics in both hemispheres. Well, this change in precipitation looks the same as that. So we're getting more precipitation where there already is a lot of precipitation, and we're getting less precipitation where there already is kind of a minimum in precipitation. And the kind of the reason for that, we won't really go into this, but it just has to do with this circulation I was talking about, the Hadley cell. We expect that to kind of extend northward as it gets warmer, and so that kind of expands these dry zones. And so a phrase that you'll sometimes hear with regard to the hydrological cycle and climate change is that wet gets wetter and dry gets drier. And that can be applied. There's kind of two ways that can be applied, but that can be applied to this, where these dry regions get drier, get less precipitation as it gets warmer. And some of the wetter regions to the north or to the south of those, or at the equator, get wetter. They get more precipitation as it gets warmer. So that's the precipitation part. So looking at the evaporation part, that's what this looks like, evaporation change. And so this is defined as positive up. So a positive value over here, these mean more evaporation into the atmosphere. And so over most land areas, you see an increase in evaporation. And so that's what I was showing before, is that, you know, some locations you have, or on average, you have an increase in precipitation over land, but in most of even those locations, your increase in evaporation, what's coming out of your land, is more than what's going in, or the change in terms of what's going in. And so then you would expect in those locations to see a net drying of the land. And so we can see that in this map of soil moisture change. This is in terms of percent. And so again, it's complicated. There's like a geographical distribution that it's not the same everywhere. But over a lot of land locations, including all of the United States, all of kind of the Amazon basin, South Africa, Europe, and Mediterranean, and Australia, we see net drying of the land surface. And so kind of one of the takeaway messages here is that if you're thinking about the water cycle under climate change, you cannot only consider the precipitation part, your input, you know, flow. You also need to think about what's leaving the land. And it's really this measure of soil moisture is what matters for, you know, agriculture, for example. It's what matters for fire danger, because it's, you know, how much moisture is in your forest and your fuels doesn't just depend on what's coming in terms of precipitation. It depends on how much evapotranspiration is coming out of those plants going into the atmosphere. And so this is like, these projections have been being made kind of since climate modeling started maturing in like the 70s and 80s. And so that's why increases in fire danger are very long-standing forecasts, like for the American West, basically because climate models have for a long time projected a decrease in land moisture over our location in the West. That was the kind of basic theory. And what's important about this is this map of drying of land surfaces under global warming. But again, this is a climate model averages under a scenario that's basically 4 times more global warming than what we've seen already. So if we look at, you know, what's happened historically, I think it's interesting to like put this in context historically. We actually look at observations. We do get back to, you know, pretty low signal to noise ratio. So we're back to this plot that, like, in the future, if we emit way more greenhouse gases, then we expect to see these huge changes. But historically, under our 1 degree Celsius of warming so far, changes are not all that dramatic. And that's very good because we're a long way away from solving this, right? So, like, you know, again, the best case scenarios are to kind of limit global warming to double what we've already seen, and for that to happen, you know, level off near the end of this century. So just to look at like what's happened historically and to kind of put this into perspective, these percentages, like I've been telling you, 3% increase in precipitation per degree Celsius. What would that look like in California? So this is the division that San Jose State is in, the climate division. We kind of split up different regions into these climate divisions. And this is precipitation going back to 1895 through 2020. And so we look at, okay, what is the average precipitation in this climate division? It's around 20 inches, so 21 inches of rain every year. And we see that we have this huge kind of variability from year to year. So it can be as much as double that. So 107% increase compared to the average for this particular year, 1983, looks like. And why did that happen? I don't, probably El Nino or something, I don't know exactly why, but it's random. It's because the ocean atmosphere system is kind of moving heat and energy and moisture around. It's not any grand reason. And then you can also have very large, decreases in your precipitation. So 2014 was kind of the center of the most recent drought, and it's kind of, we don't, depending on how you define it, we could talk about this year being part of a larger scale drought, but a lot of times it gets kind of boxed into 2011 to 2015 was our drought year. But 2014 anyway, 81% drop in precipitation in this division. And so if we just assume that precipitation in California was increasing with the average over the land, this is what the climate change signal would look like, plus 3% over that time period. And this is not necessarily to say that precipitation is supposed to increase over California. I'll show you in the next slide. It's actually supposed to not change, essentially. But what this is illustrating is kind of how small that climate change signal is in terms of precipitation relative to just natural variability that you see from year to year, at least how large that signal is, so far. So this is what, this is the same type of plot, it's just a slightly different location. So this is just for San Jose, California. This is total precipitation for each year going back to 1950. And we have historical data in gray, and then climate model projections under 2 emission scenarios out to 2100. And so we see that climate models in San Jose do not project changes in precipitation in our region. So we're in kind of one of these regions we're kind of like between, we can go back to this map of change. We're like right on this border of, it's supposed to dry to our south and supposed to, precipitation is supposed to increase to our north. And so we're kind of right here where it doesn't change basically at all, or at least that's the projection. So that means that like our 2014 drought, if there is a contribution from climate change to that, it wouldn't be in the precipitation side of things. It might be on the evaporation side of things. So it's warmer, it's for sure warmer than it would be otherwise. And so there will be more water going into the atmosphere than there would be otherwise. And so that's the type of thing that scientific studies on that drought have shown. So here's just an example of that. Causes of the 2011 to 2014 California drought. And they say models, so climate models project rising greenhouse gases to cause changes in California all winter precipitation that are very small compared to the recent drought anomaly. So they're saying that any projections, these projections are small compared to, look how big this reduction in precipitation was in 2014. But, however, a long-term warming trend likely contributed to surface moisture deficits during the drought. So that's that increase in evaporation component of things. And so just to kind of show a couple other representations of the drought, like the 2014 drought, we want to put in longer term context. And so there's been a lot of papers that look at, for example, tree rings that you can look at, trees that are sensitive to moisture, and so then their rings are thicker or less thick depending on how much rain you get any given year. And so that's what this reconstruction is, back to the year 800, trying to reconstruct drought. This is Palmer Drought Severity Index. So it's just a number that when it's negative, it means more droughty, more dry, and when it's positive, it's wetter. And so they're looking at, here is the 2014 drought compared to like a longer time context, because we saw in our previous graph that it was unprecedented in terms of rainfall back to the 1890s. And then here's another, this is our drought index again. So unprecedented back to the 1890s. But if you go back further in time, we did see, looks like, at least within uncertainty ranges, that we had years like that. So if there is a climate change signal, and we do think there's a climate change signal in terms of the evaporation, if not in the precipitation component of that, it's not extremely large, and it's not something that like radically shifts the probability of a situation like that. And that's what we see globally and in the United States in terms of droughts as well. So this is the United States, and this is the fraction of the United States that's defined as very wet or very dry. And I forget the exact threshold they're using, I guess, 90 percentile. And so we don't really see major trends. These are not, hockey sticks in terms of the hydrological cycle, in terms of the fraction of area that's very wet or very dry. And globally, this is changes in global drought. Again, it's the way that they're expressing this is how much of the land surface area is in various categories of this Palmer Drought Severity Index. How much is in extreme drought, severe drought, moderate drought, and we don't see a trend in that yet either. So these hydrological cycle changes, that's expected. That's not like that's something that climate scientists said there should be these huge increases and we're not seeing it. The basic theory is it changes by 3% per degree, and then you're kind of you're looking at 3% increase in precipitation and 4.5 increase in evaporation, and so you're getting this kind of small difference that's embedded in the noise of natural variability. And so so far, that's not a signal that just jumps out at you from the data, but it is something that if you are on one of these large emissions trajectories in the future, that then it really emerges, later in the century and becomes a huge issue. And then you do start to see, these return periods and things change dramatically.